The true scale of the first ancient galaxies is often imagined in a very particular way. Many people, including scientists for a long time, have pictured the earliest galaxies as small, faint collections of stars, barely holding together in a young and simple universe. In this familiar view, the early cosmos is quiet and modest, with structures slowly and cautiously taking shape, far smaller and less complex than the galaxies we see around us today. This assumption feels intuitive, because it matches the idea of gradual growth, of simple beginnings leading step by step toward the vast and structured universe we now observe. Yet even within this common understanding, there has always been a sense of uncertainty. The early universe is distant not only in space, but also in time, and for many years our observations of it were limited. Astronomers relied on indirect measurements, faint signals, and theoretical models that filled in the gaps where direct evidence was missing. As a result, the picture of the first galaxies remained somewhat blurred, shaped as much by expectation as by observation. Different models suggested different sizes, different rates of growth, and different levels of organisation, all within a narrow range that still felt comfortably small and restrained. What has become clearer, especially in recent years, is that this early phase of cosmic history is more nuanced than those early assumptions suggested. The formation of the first galaxies was not a single event, nor a uniform process unfolding the same way everywhere. Instead, it was a gradual and layered development, influenced by local conditions, the distribution of matter, and the subtle balance between gravity, radiation, and time. Understanding this requires patience, because the signals we observe today carry the imprint of billions of years of travel through an expanding universe. This video will explore that understanding slowly, without rushing toward conclusions. Rather than treating the first ancient galaxies as tiny, primitive placeholders for what would come later, we will examine how their true scale emerges from careful observation and measured interpretation. We will move layer by layer, staying close to what the data actually show and allowing each idea to settle before moving on. There is no single moment of revelation here, only a steady refinement of perspective. Welcome to AstraFlow. Here, science drifts quietly, and understanding comes without effort. If you would like to share your thoughts or quietly follow along in future explorations, you are always welcome to do so. Now, let's begin. To start, it helps to place ourselves gently in time. The first ancient galaxies did not appear immediately after the universe began. After the Big Bang, there was an extended period often called the Cosmic Dark Ages, when the universe was filled mostly with neutral hydrogen gas and light could not yet travel freely. No stars had formed, and there were no galaxies in the sense we use the word today. Space was expanding and cooling, and matter was slowly responding to the pull of gravity, gathering into slightly denser regions. When we speak of the first galaxies, we're referring to a span of time several 100 million years after the beginning, when these denser regions became structured enough to ignite sustained star formation. Even this description hides complexity. There was no sharp boundary between before galaxies and after galaxies. Instead, there was a gradual transition as small collections of stars began to form, merge, and organize within larger gravitational frameworks dominated by dark matter. For a long time, astronomers assumed that these early structures must have been extremely small. The reasoning was straightforward. With less time available, and with the universe still relatively young, it seemed reasonable that galaxies would not yet have accumulated much mass. Their stars were thought to be few, their shapes irregular, and their overall scale modest. In this view, large galaxies like the Milky Way were the result of billions of years of slow assembly, built up from countless small predecessors. This assumption shaped both observation and theory. Telescopes prior to the James Webb Space Telescope could detect only the brightest and most extreme objects at great distances. Anything faint or diffuse remained invisible, reinforcing the idea that early galaxies were mostly small and dim. Theoretical models, in turn, were calibrated to match these limited observations, producing a consistent but incomplete picture. As we move forward in this series, we'll see how new data have begun to gently stretch that picture, not by overturning it abruptly, but by adding detail where there was once only outline. The true scale of the first ancient galaxies is not simply a matter of size in kilometres or mass in stars. It is also about how quickly structure can emerge, how efficiently matter can organise itself, and how our own tools of observation shape what we believe to be possible. For now, it is enough to rest with the familiar idea while allowing space for adjustment. The early universe was not empty, nor was it static. It was active in a quiet way, governed by slow processes that left subtle traces in the light we detect today. By following those traces carefully, we can begin to sense the true dimensions of the first galaxies, not as imagined limits, but as measured realities that continue to come into focus. After the universe's earliest moments had passed, and expansion had begun to smooth out its initial extremes, there came a long, quiet interval often referred to as the cosmic dark ages. During this time, space was filled almost entirely with neutral hydrogen and helium gas, spread thinly but steadily as the universe continued to grow. There were no stars yet to shine, no galaxies to define structure, and no sources of light capable of travelling freely through space. From our current perspective, this period can feel empty, but in reality, it was active in a subtle and persistent way, shaped by gravity working patiently over immense distances. In this early environment, matter was not evenly distributed. Tiny variations in density, left over from the universe's earliest phases, began to matter more and more as time passed. Regions that were slightly denser than their surroundings exerted a stronger gravitational pull, slowly drawing in nearby gas and dark matter. This process was not fast, and it was not dramatic. It unfolded over tens and then hundreds of millions of years, with matter drifting inward at speeds that, by human standards, would seem almost imperceptible. Dark matter played a central role during this phase. Although it does not emit or absorb light, it outweighs ordinary matter by a large margin and responds strongly to gravity. As the universe expanded and cooled, dark matter formed broad, diffuse halos, providing gravitational frameworks that ordinary gas could settle into. These halos did not immediately produce visible structures, but they defined the regions where future galaxies would eventually take shape. In this sense, the first ancient galaxies were outlined long before they became luminous. As gas accumulated within these dark matter halos, it began to cool. Cooling is essential, because only when gas loses energy can it collapse further and increase in density. In the early universe, cooling occurred primarily through simple atomic processes involving hydrogen and helium. These mechanisms were less efficient than the cooling pathways available later, when heavier elements existed, but they were sufficient to allow gradual contraction. Over time, pockets of gas within the halos became dense enough to begin forming stars. This transition marked the end of the Dark Ages and the beginning of what is often called the Cosmic Dawn. Light from the first stars started to appear, slowly altering the surrounding environment. Ultraviolet radiation from these stars began to ionize nearby hydrogen, changing how light moved through space and making the universe increasingly transparent. This was not a sudden illumination of the cosmos, but a patchwork process, with small regions lighting up while others remained dark. From a structural point of view, this era is where the earliest galaxies began to exist as identifiable systems. However, they did not yet resemble the well-defined spirals or ellipticals familiar to us today. Instead, they were collections of stars embedded in gas-rich environments, still closely tied to the dark matter halos that governed their overall shape and extent. Their boundaries were not sharp and their internal organisation was still evolving. What matters here is scale. Even at this early stage, the regions involved were vast. The halos that hosted the first galaxies could span thousands of light years or more, even if the luminous portions within them were smaller. This means that from the very beginning, galaxies were not isolated points, but extended structures, connected to their surroundings through gravity and the flow of matter. The universe did not build galaxies from tiny seeds alone. It built them within large-scale frameworks that were already in place. As we let this idea settle, it becomes easier to see why early assumptions about very small, simple galaxies may have missed part of the picture. The Dark Ages were not a blank pause between creation and complexity. They were a formative period, quietly establishing the scales on which later structures would grow. By the time the first stars ignited, much of the underlying architecture of the universe was already defined. In the next part, we will look more closely at what scientists mean when they refer to the first galaxies, and why this term describes a gradual emergence rather than a single, clearly defined beginning. For now, it is enough to remain in this early universe where structure is forming slowly, light is just beginning to appear, and scale is already larger than it might first seem. When scientists speak about the first galaxies, the phrase can sound more definite than it truly is. It suggests a clear starting point, a moment when galaxies suddenly appeared and could be cleanly identified. In practice, the concept is softer and more gradual. The first galaxies are not defined by a single event or a strict boundary in time, but by a slow transition in which collections of matter begin to behave like long-lived, self-gravitating systems capable of forming stars over extended periods. In the early universe, there were many structures that existed somewhere between isolated star-forming regions and fully developed galaxies. Some were small, short-lived groupings of stars that formed and faded without leaving a lasting imprint. Others grew more steadily, held together by deeper gravitational wells provided by dark matter halos. What we call the first galaxies are those systems that crossed a certain threshold of stability, where star formation could continue rather than quickly shutting down. This threshold was not the same everywhere. Local conditions mattered. The density of surrounding gas, the mass of the dark matter halo, and the influence of nearby radiation fields all played a role in determining whether a structure could persist. As a result, the earliest galaxies formed over a span of time rather than at a single cosmic moment. Some appeared earlier, in regions where matter was already more concentrated. Others emerged later, following similar processes but on slightly delayed schedules. Because of this, the phrase first galaxies is best understood as a category, rather than a precise label. It refers to a population of early systems that share certain characteristics: sustained star formation, a measurable mass, and a gravitational structure that allows them to grow and interact with their environment. These characteristics did not switch on all at once. They developed gradually, overlapping with one another as the universe evolved. From an observational perspective, this gradual emergence presents challenges. When we detect light from extremely distant objects, we are seeing them as they were billions of years ago, often at a time when their internal structures were still changing. A system that appears small and compact in one observation might later merge with others, becoming part of a larger galaxy. Another might shine brightly for a short time and then fade. Deciding which of these should be counted among the first galaxies requires careful interpretation. This is where scale becomes especially important. The first galaxies were not defined solely by the number of stars they contained, but by the extent of their gravitational influence. Even if the luminous portion of a young galaxy was relatively compact, the region over which it gathered gas and interacted with its surroundings could be much larger. In this sense, the true scale of these early galaxies extends beyond what is immediately visible. It is also important to note that early galaxies were not isolated experiments scattered randomly through space. They formed within a cosmic web of filaments and nodes shaped by dark matter. Gas flowed along these filaments, feeding growing structures and linking them to one another. This network influenced both where galaxies formed and how large they could become, even at very early times. As this idea settles, the notion of the first galaxies shifts slightly. They are no longer imagined as tiny lonely objects flickering briefly in a vast darkness. Instead, they appear as early participants in a larger pattern, shaped by forces and structures that operated on scales already immense. Their beginnings were modest in some respects, but the context in which they formed was anything but small. In the next part, we will look more closely at how matter gathered in early space and how gravitational processes set the stage for the growth of these first enduring galactic systems. For now, it is enough to rest with the understanding that the first galaxies were not defined by sharp lines, but by a slow crossing from temporary structure into lasting form. To understand how the first galaxies began to take shape, it helps to focus on the slow gathering of matter in early space. After the cosmic dark ages, the universe was still relatively simple in composition, made mostly of hydrogen, helium, and dark matter. What gave rise to structure was not sudden motion or violent interaction, but the steady influence of gravity acting over long periods of time. Matter moved because it was slightly unevenly distributed, and gravity responded to those differences without urgency. In regions where dark matter had already formed broad halos, ordinary gas began to drift inward. This inward motion was gentle and continuous. Gas did not fall freely in dramatic collapses, but instead followed gradual paths shaped by the overall gravitational landscape. As more material accumulated, the central regions of these halos became denser, and the pace of gathering increased slightly, though it remained slow on human timescales. This process defined the initial outlines of what would later be recognized as galaxies. An important feature of this stage is that scale was established early. Dark matter halos could extend across vast regions, even before any stars formed within them. The luminous components that would eventually appear were only a fraction of the total structure. This means that when we think about the size of the first galaxies, we need to consider not only where stars were forming, but also the much larger regions where matter was being organized and held together by gravity. As gas flowed inward, it began to interact with itself. Collisions between gas particles allowed energy to be redistributed and in some cases radiated away. This loss of energy made it possible for gas to settle into dense configurations. Over time, these denser regions became the sites where stars could form. However, the process was uneven. Some regions accumulated gas efficiently and moved steadily towards star formation, while others remained diffuse and inactive for much longer. Throughout this period, the surrounding environment played a crucial role. Gas did not arrive from all directions equally. It tended to follow the filaments of the cosmic web, flowing along preferred paths shaped by the distribution of dark matter. These filaments connected, forming galaxies to larger structures, supplying them with material and influencing their eventual growth. Even at this early stage, galaxies were part of a connected system rather than isolated islands. This gradual gathering of matter also meant that early galaxies were dynamic. Their boundaries shifted as gas continued to arrive, and as interactions with nearby structures altered the local gravitational field. There was no fixed edge, no clear moment when a galaxy became complete. Instead, there was continuous adjustment, with matter moving inward, settling, and sometimes being redistributed by internal processes. What becomes clear when we look closely at this phase is that the foundations of galactic scale were laid before galaxies were fully visible. By the time the first sustained star formation occurred, the regions involved were already extensive. The luminous portions we observe today are only the most visible markers of a much larger and older process of assembly. As this idea settles, the image of early galaxies grows quieter and more expansive. Their beginnings were not marked by sudden brilliance, but by patient accumulation. Gravity worked steadily, matter responded slowly, and scale emerged naturally from this interaction. In the next part, we will turn our attention to the onset of sustained star formation and how it shaped the earliest visible phases of galactic life. As matter continued to gather within the gravitational frameworks established earlier, certain regions reached conditions where star formation could begin and persist. This moment did not arrive suddenly or uniformly. Instead, it emerged gradually as gas became dense enough and cool enough for gravity to overcome internal pressure. In the early universe, this balance was delicate. Gas was warmer than it would be later in cosmic history, and the mechanisms available for cooling were limited. Even so, in the densest pockets of gas, the slow contraction continued. The first sustained star formation occurred within these compact regions, embedded deep inside larger dark matter halos. Gas clouds fragmented into smaller clumps, each gradually collapsing under its own gravity. As density increased, temperatures rose locally, eventually reaching the point where nuclear fusion could begin in the cores of newly formed stars. These first generations of stars were not isolated events. They formed in groups, creating early stellar populations that marked the visible emergence of galaxies. What distinguishes sustained star formation from earlier, more transient episodes is continuity. In some early structures, stars formed briefly and then stopped, as radiation and energetic processes pushed remaining gas away. In the first true galaxies, however, the gravitational potential was deep enough to retain gas despite the energy released by young stars. This allowed star formation to continue over longer periods, giving these systems stability and persistence. Even at this stage, scale remains a central theme. The regions where stars formed were small compared to the full extent of the dark matter halo, but they were embedded within much larger reservoirs of gas. This surrounding material served as a long-term supply, slowly feeding further star formation. As a result, the visible size of a young galaxy did not fully represent its true physical scale. Much of its mass and influence extended far beyond the regions where light was being produced. The stars themselves also shaped their environment. Radiation from the earlier stars began to alter the surrounding gas, heating it and changing its state. In some cases, this slowed further star formation locally, while in others it triggered additional collapse in nearby regions. These interactions were complex but generally unfolded over long timescales, contributing to gradual growth rather than rapid transformation. From an observational perspective, this phase is especially important. The light from these first sustained stars is what allows us to detect early galaxies at all, yet that light carries only partial information. It tells us where stars were forming, but not the full extent of the structures that supported them. Understanding the true scale of early galaxies therefore requires combining what we see with models of the unseen components that surround and shape them. As we pause with this idea, the first ancient galaxies begin to feel less like brief sparks in darkness, and more like steady evolving systems. Their earlier stars marked a visible beginning, but that beginning rested on foundations laid much earlier and spread across much larger regions of space. In the next part, we will consider how scientists before the era of James Webb expected these early galaxies to look and how those expectations shaped our understanding. Before the James Webb Space Telescope began returning its observations, scientific expectations about the first ancient galaxies were shaped by a combination of theory and limited data. Astronomers relied on earlier space telescopes and ground-based instruments that could glimpse the distant universe only in narrow ways. These tools were powerful for their time, but they struggled to detect faint, faraway objects whose light had been stretched deep into the infrared by cosmic expansion. As a result, much of what was believed about early galaxies was inferred rather than directly seen. The prevailing model suggested that galaxies in the first billion years of the universe would be relatively small and inefficient at forming stars. In these models, growth was slow and hierarchical. Tiny systems formed first, then merged gradually over long spans of time, building up larger galaxies step by step. Star formation was expected to be sporadic, limited by the availability of cool gas and easily disrupted by the energy released from young stars. This picture felt consistent with a universe still finding its structure. These expectations influenced how data were interpreted. When faint objects were detected at extreme distances, they were often assumed to be small by default. Brightness was taken as a rough proxy for size and mass, and dim signals were associated with modest systems. Even when uncertainties were acknowledged, the general assumption remained that the early universe was populated mainly by numerous small galaxies, rather than fewer large ones. Another factor shaping these expectations was computational modelling. Simulations of cosmic structure formation had to balance complexity with practicality. Many early simulations favoured conservative assumptions about how quickly gas could cool and how efficiently stars could form in young halos. These choices produced galaxies that grew steadily but cautiously, reinforcing the idea that large, massive systems required long periods of accumulation. None of this was unreasonable. Science often advances by building models that fit the best available evidence, then refining them as new data arrive. Before James Webb, there was no strong observational reason to believe that very early galaxies could already be large or luminous. The absence of evidence was not evidence of absence, but it did guide expectations toward simplicity. As we let this perspective settle, it becomes clear how strongly our understanding is shaped by the tools we use. The image of the early universe as a place of small, faint galaxies was not born from certainty, but from careful extrapolation. It provided a stable framework within which questions could be asked and predictions made. In the next part, we will see how new observations began to gently expand that framework, adding detail where there was once only assumption. When the James Webb Space Telescope began its observations, it did not immediately rewrite our understanding of the early universe. Instead, it added clarity in places that had long been indistinct. Designed to observe in the infrared, James Webb could detect light that had travelled for more than 13 billion years, stretched by cosmic expansion into wavelengths invisible to earlier instruments. This capability allowed astronomers to observe galaxies forming much closer to the beginning of cosmic history than had previously been possible. What James Webb sees is not fundamentally different light, but older light, arriving with more of its original information intact. Earlier telescopes often captured only the brightest portions of distant objects, missing fainter extended structures. With its sensitivity, James Webb can trace both concentrated regions of star formation and the surrounding glow of stars and gas that extend farther outward. This broader view changes how size and brightness are interpreted. In practical terms, this means that early galaxies no longer appear as isolated points against darkness. Many are resolved as extended systems, with measurable structure even at very high redshifts. Their light profiles suggest distributions of stars that span larger regions than expected, and their overall brightness implies more stellar mass than earlier models predicted for such young systems. These observations do not stand alone. They're consistent across multiple fields of view and independent analyses. Importantly, James Webb does not observe these galaxies as finished objects. What it reveals are moments in their ongoing formation. Some appear compact and intense, while others show broader, more diffuse structures. This variation indicates that early galaxies followed multiple growth paths, even within the same epoch. Scale, in this context, is not a single number, but a range shaped by local conditions and history. Another subtle shift introduced by these observations is confidence. Where earlier detections were tentative and rare, James Webb provides repeated, consistent measurements. This allows astronomers to compare galaxies across similar distances and times, identifying patterns rather than relying on isolated examples. As a result, conclusions about size and mass are now grounded in populations rather than exceptions. As this understanding settles, the role of James Webb becomes clear. It does not declare that early galaxies were unexpectedly large in a dramatic sense. Instead, it shows that our previous view was incomplete. The true scale of the first ancient galaxies includes both their visible stars and the extended structures that support them, structures that were simply beyond reach before. In the next part, we will look more closely at one of the most striking aspects of these observations: the brightness and apparent size of some very early galaxies, and how scientists interpret these measurements without rushing to conclusions. One of the first qualities scientists noticed in James Webb's observations of very early galaxies was their brightness. At distances corresponding to only a few 100 million years after the beginning of the universe, some galaxies appeared brighter than models had anticipated. Brightness, however, is a subtle measure. It does not directly tell us how large a galaxy is, nor does it provide a simple reading of mass. Instead, it reflects how much light is being produced and how that light is distributed across space. In the early universe, brightness can arise from several overlapping factors. A galaxy may appear bright because it contains many stars, or because its stars are forming rapidly, or because those stars are particularly massive and short-lived, emitting large amounts of light in a short time. James Webb's sensitivity allows astronomers to distinguish between these possibilities more carefully than before, by examining the colour, spread and intensity of the light across each object. What becomes apparent is that brightness alone does not imply an extreme or unusual state. Some early galaxies are bright because they are efficiently forming stars across extended regions. Others are bright because their light is concentrated in compact cores, surrounded by fainter structures that extend outward. In both cases, the total luminous output suggests systems that are already well established, rather than tentative or transient. Size measurements add another layer to this picture. By analysing how light fades from the centre of a galaxy toward its edges, astronomers can estimate how far stars are spread. James Webb has shown that in several cases this spread is larger than previously expected for such early times. The visible portions of these galaxies can span thousands of light years, even when the universe itself was still very young. Interpreting these measurements requires care. Distance, dust, and observational limits all affect how size and brightness are perceived. Scientists do not take a single image as definitive proof. Instead, they compare many observations, apply consistent methods, and test their conclusions against models that include both visible matter and dark matter. Through this process, the idea emerges that early galaxies may have assembled mass and structure more efficiently than earlier models allowed. This does not mean that all early galaxies were large or luminous. Many remain small and faint, just as expected. What has changed is the range of possibilities. The early universe now appears capable of producing a wider diversity of galactic scales, even within a relatively short span of time. Some systems grew quickly, others slowly, and both paths left traces that we can now observe. As this understanding settles, the initial surprise gives way to a quieter recognition. The brightness and size of some early galaxies are not anomalies demanding dramatic explanations. They are data points within a broader, more flexible picture of cosmic growth. In the next part, we will look at how scientists measure scale across time itself, translating ancient light into present-day understanding without compressing complexity into simple numbers. Measuring the scale of galaxies that existed billions of years ago requires a careful translation between what is observed and what is inferred. The light captured by telescopes like James Webb has travelled across an expanding universe, stretched and altered by time itself. What we see is not a direct snapshot, but a record encoded in wavelength, brightness, and spatial distribution. Turning that record into a sense of physical size and mass involves a series of measured steps rather than a single calculation. One of the first considerations is distance. In cosmology, distance is tied closely to redshift, a measure of how much the universe has expanded since the light was emitted. Higher redshift corresponds to earlier times. Using well-tested models of cosmic expansion, astronomers can estimate how far away a galaxy is and, by extension, how old the light is that we are seeing. This provides a temporal context. placing each observation along the timeline of the universe. Once distance is established, apparent size on the sky can be converted into a physical scale. A galaxy that appears as a small blur in an image may, at great distance, actually span thousands of light years. This conversion depends on the geometry of the universe and on precise measurements of angular size. James Webb's resolution makes it possible to trace how light is distributed across these distant objects, offering more reliable estimates than were previously available. Brightness is treated with similar care. Observed light must be corrected for distance and for the stretching of wavelengths. Astronomers examine the spectrum of a galaxy's light to determine the types of stars contributing to it and their likely ages. From this, they can estimate how much stellar mass is present. These estimates are not exact, but they are grounded in well-understood relationships between stellar populations and the light they emit. Crucially, scientists do not rely on a single method. Size estimates from light profiles are compared with mass estimates from stellar modelling, and both are checked against expectations from dark matter theory. If these independent lines of evidence align, confidence grows. If they diverge, assumptions are revisited. This process is iterative and cautious, favouring stability over rapid reinterpretation. What emerges from this careful measurement is a picture in which some early galaxies occupy a surprising position on the scale spectrum. They are not as massive as present-day large galaxies, but neither are they as small as once assumed. Their sizes and masses place them in an intermediate category, already substantial yet still evolving. This fits naturally with a universe in which structure formation can proceed efficiently under the right conditions. As we pause here, it becomes clear that scale is not something directly seen, but something patiently reconstructed. Each estimate carries uncertainty, but together they form a coherent pattern. In the next part, we will explore how quickly these early galaxies were able to grow and what their growth rates reveal about the conditions of the young universe. When the scale of early galaxies is placed alongside estimates of their age, another question naturally settles into view. How quickly did these systems grow? Growth rate is not about sudden expansion or dramatic change, but about how efficiently matter was converted into stars over time. In the early universe, time itself was a limited resource. A galaxy observed a few 100 million years after the beginning had only that span to gather gas, form stars, and develop structure. Observations suggest that some early galaxies were forming stars at steady and sustained rates. Rather than brief, intense bursts followed by long quiet periods, these systems appear to have maintained ongoing star formation. This does not imply constant intensity, but it does indicate continuity. Gas flowed in, stars formed, energy was released, and yet enough material remained bound for the process to continue. This steady behaviour supports the idea that their gravitational frameworks were already well established. Growth rate also depends on supply. In the young universe, gas was abundant and relatively pristine, composed mostly of hydrogen and helium. For galaxies embedded within dense regions of the cosmic web, this gas could be replenished continuously. Filaments funneled material inward, allowing galaxies to increase their mass without relying solely on mergers. This form of smooth accretion supports gradual but effective growth over extended periods. Comparisons with later galaxies reveal an important contrast. In the more mature universe, star formation can be limited by feedback processes, by depleted gas supplies, or by environmental effects. Early galaxies operated under different conditions. Their surroundings were richer in available material, and the overall cosmic environment favoured assembly. As a result, growth rates that might seem high by later standards were natural outcomes of early conditions. It is important to note that growth was not uniform across all early galaxies. Some remained small, forming stars slowly or intermittently. Others grew more quickly, becoming relatively massive in a short span of cosmic time. This diversity reflects differences in local environment rather than a single universal pathway. Scale, once again, emerges as a range rather than a fixed expectation. As this understanding settles, the apparent efficiency of early galaxy growth feels less surprising. Given the abundance of material and the supportive structure of the young universe, steady growth was not only possible but likely in certain regions. In the next part, we will look inside these young galaxies, examining the internal structures that observations suggest were already taking shape. Looking inside the earliest galaxies, as far as observations allow, reveals that structure began to emerge sooner than once assumed. These young systems were not always shapeless clouds of stars. In many cases, their light shows patterns that suggest internal organization, even while the galaxies were still forming. This organization does not imply mature spiral arms or stable disks, but it does indicate that gravity was already arranging matter in coherent ways. James Webb's images often show variations in brightness within early galaxies. Some regions appear more concentrated, while others extend outward more gradually. These differences can reflect uneven star formation, where some areas are more active than others. Over time, such variations can lead to recognizable internal features, setting the stage for later structural development. The presence of internal structure also speaks to scale. For structure to exist, a system must be large enough and stable enough for gravity to act over extended periods. If early galaxies were extremely small or short-lived, such organization would be difficult to maintain. The fact that structure is observed suggests that many of these galaxies had already reached a scale where internal dynamics could unfold slowly rather than being immediately disrupted. Gas played a central role in shaping these structures. As stars formed, they influenced surrounding gas through radiation and gentle outflows. In some regions, this interaction redistributed material, smoothing density differences. In others, it created new pockets of higher density, encouraging further star formation. These processes contributed to an evolving internal landscape rather than a static one. Importantly, the structures observed are consistent with gradual assembly. They do not require sudden or extreme events. Instead, they fit within a framework where gas flows, star formation, and gravity interact continuously. This continuity reinforces the idea that early galaxies were not fleeting experiments, but enduring systems developing complexity over time. As we rest with this picture, the first ancient galaxies begin to feel less distant in character, even if they remain distant in time. Their internal evolution follows principles that still operate in galaxies today, though under different conditions. In the next part, we will consider the limits of our current interpretations and why caution remains essential when translating observation into certainty. Even with the clarity provided by modern observations, there are important limits to how confidently we can interpret the earliest galaxies. The light we receive from them is faint, stretched, and shaped by vast distances. Every measurement carries uncertainty, not as a flaw, but as an inherent part of observing a universe in motion. Recognizing these limits is essential to understanding scale without overextending conclusions. One source of uncertainty comes from how light traces mass. Stars produce light, but much of a galaxy's mass lies in forms that do not shine directly, such as gas and dark matter. When we estimate size or mass based on light alone, we are always working with a partial picture. Models help bridge this gap, but models rely on assumptions that must be tested and refined over time. Another limitation arises from resolution. Even with James Webb's capabilities, the smallest details within distant galaxies remain blurred together. What appears as a single extended region of a light may, in reality, be a collection of smaller structures too close to distinguish. This means that inferred sizes can depend on how light is distributed and how that distribution is interpreted. Different analysis methods can yield slightly different results, all within reasonable bounds. Time itself introduces another layer of complexity. Observations capture galaxies at specific moments in their evolution, not across their full lifespans. a galaxy observed during an active phase of star formation may appear larger or brighter than it would at a quieter time. Without knowing its full history, scientists must interpret each snapshot carefully, avoiding assumptions about permanence. Because of these factors, scientific understanding advances through accumulation rather than declaration. Individual observations are compared, patterns are identified, and conclusions are adjusted gradually. When data challenge earlier expectations, the response is not immediate replacement, but careful integration. This approach maintains continuity in knowledge while allowing it to expand. As this perspective settles, it becomes clear that uncertainty does not weaken the study of early galaxies. Instead, it provides context. It reminds us that scale is not a fixed answer waiting to be revealed, but a measured relationship between observation and interpretation. In the next part, we will see how these careful adjustments lead to revisions in cosmic timelines, gently reshaping how we understand the early growth of galaxies. As observations of early galaxies accumulate and interpretations are refined, one of the areas most affected is the cosmic timeline. Timelines in astronomy are not rigid schedules, but frameworks that describe when certain processes become common or dominant. The emergence of galaxies is one such process, and new data have prompted scientists to adjust these frameworks with care rather than abrupt change. Earlier timelines placed the formation of substantial galaxies somewhat later in cosmic history, assuming that long periods were required for mass to accumulate. With improved observations, it has become clear that some galaxies reach significant size earlier than expected. This does not compress the entire history of galaxy formation into a shorter span, but it does broaden the range of when different scales of structure could appear. These revisions are subtle. They do not suggest that the universe evolved faster overall, but that local conditions allowed certain regions to develop more quickly. Dense areas of the cosmic web provided favourable environments for early growth, while other regions remained comparatively quiet. Timelines now reflect this diversity, accommodating multiple pathways rather than a single sequence. Importantly, adjusting a timeline does not invalidate what came before. Earlier models successfully described many aspects of cosmic evolution and remain useful. The changes introduced by new data refine these models, aligning them more closely with observation. This process illustrates how scientific understanding evolves through continuity rather than disruption. As we rest with this idea, the early universe appears more flexible and varied than once imagined. Structure formation was not bound to a strict schedule, but unfolded across a range of times and scales. In the next part, we will connect the first ancient galaxies to the later, more familiar galaxies of today, tracing continuity rather than contrast. The first ancient galaxies did not exist in isolation from what came after them. They are part of a continuous chain of development that leads, over billions of years, to the galaxies we observe in the present universe. Understanding their true scale involves seeing them not as primitive outliers, but as early stages within an ongoing process of growth, interaction, and transformation. As time passed, early galaxies continued to gather material from their surroundings. Some merged with neighbouring systems, while others grew more quietly through steady inflows of gas. These processes gradually increased their mass and altered their structure. Over long periods, repeated interactions smoothed irregularities and redistributed stars and gas, guiding galaxies toward more stable configurations. The scale of modern galaxies carries the imprint of these early phases. Features such as extended halos, thick stellar components, and broad distributions of dark matter all have roots in the conditions of the early universe. Even though present-day galaxies are far larger and more complex, their foundations were established when the universe was still young. In this sense, the first galaxies were already participating in shaping the future structure of the cosmos. This continuity also helps explain why early galaxies could achieve substantial size. They were not starting from nothing, nor were they constrained by simple beginnings. they formed within a universe already structured on large scales, where gravity had ample opportunity to organise matter. The apparent efficiency of their growth becomes more understandable when viewed as part of a long, uninterrupted sequence. As we allow this connection to settle, the distance between the ancient and the familiar begins to narrow. The first galaxies are no longer abstract or remote. They are ancestors, linked to present structures through gradual change rather than sudden leaps. In the next part, we will step back slightly to look for broader patterns in how galaxies assemble over time, keeping our focus on scale and process. When we step back from individual galaxies and look across long spans of cosmic time, broader patterns of assembly begin to appear. These patterns are not strict rules, but recurring tendencies shaped by gravity, available matter, and the expanding universe itself. From the earliest epochs onward, galaxies tend to grow in ways that balance accumulation and redistribution, slowly adjusting their scale rather than changing abruptly. One consistent pattern is that structure forms from the outside and the inside at the same time, but at different rates. Dark matter establishes large-scale frameworks early, creating extended regions of influence. Within these regions, gas responds more slowly, cooling, settling, and forming stars over time. This layered growth means that a galaxy's true scale often exceeds what is immediately visible, especially in its early stages. The luminous core may be compact, while the surrounding gravitational structure is already broad. Another pattern involves efficiency. Under the conditions of the young universe, some galaxies converted gas into stars more effectively than others. This efficiency was influenced by environment, with denser regions supporting faster growth. Over time, these differences accumulated, producing a wide range of galaxy sizes even at similar ages. Scale, therefore, is not simply a function of time, but of place within the cosmic web. Mergers also follow a recognizable rhythm. Early in cosmic history, interactions between galaxies were more common, as distances were smaller and structures more closely packed. These encounters did not always lead to dramatic change. Often, they resulted in gradual blending, where mass increased and structure became more stable. Such processes contributed to steady expansion rather than sudden transformation. As this broader view settles, the first ancient galaxies appear as part of a repeating pattern rather than an exception. Their scales fit naturally within a universe that builds complexity through accumulation, interaction, and time. In the next part, we will slow further and reflect on scale itself as a concept, especially when applied to a universe that is constantly evolving. When we speak about scale in the context of the early universe, it helps to loosen the expectation that scale must be fixed or immediately comparable to what we see today. Scale is not a single measurement that applies equally at all times. It is a relationship between size, mass, time, and environment, all of which were changing together in the young cosmos. In this sense, scale is something that emerges gradually, becoming clearer as structures persist and interact. In the earliest galaxies, scale was defined less by sharp boundaries and more by influence. A young galaxy's reach extended as far as its gravity could guide gas and stars, even if only a small portion of that region was actively producing light. This means that two galaxies with similar visible sizes could differ significantly in their true extent, depending on how much mass surrounded them and how strongly it was bound. As time progressed, these differences became more apparent. Systems that were able to maintain steady growth gradually expanded their effective scale, both by forming stars internally and by drawing in material from their surroundings. Others remained smaller, limited by environment or internal processes. The concept of scale therefore shifted from potential to expression, from what a system could become to what it visibly was. Applying modern definitions of size too strictly to these early systems can be misleading. A galaxy that appears compact, by today's standards, may have been substantial within the context of its era. its scale should be understood relative to the density, temperature, and structure of the universe at that time. When viewed this way, the early galaxies observed by James Webb occupy a meaningful position along a continuous spectrum of growth. As this idea settles, scale becomes less about comparison and more about context. The first ancient galaxies were neither unusually large nor unusually small. They were appropriately scaled to their moment in cosmic history. In the next part, we will gently connect this evolving sense of scale to the roles of time and distance in observation, keeping our focus steady and grounded. Time and distance are inseparable when we observe the earliest galaxies. Every image we receive is shaped by the journey light has taken, moving through an expanding universe for billions of years before reaching our instruments. This means that distance is not only a measure of how far away something is in space, but also how far back it exists in time. The earliest galaxies are seen at moments when their structures were still forming, their scale still in motion. Because of this, observation is always selective. We do not see the full lifespan of a galaxy, but a brief interval within it. Two galaxies at similar distances may be at slightly different stages of development, simply because their light was emitted at different moments. Interpreting scale requires holding this in mind, recognizing that what appears small or large is tied to when we are seeing it, not just what it will eventually become. Distance also affects how light spreads and fades. Features that are extended but faint can slip below detection, while compact, bright regions remain visible. This can make early galaxies appear more concentrated than they truly are. James Webb's sensitivity reduces this effect, but it does not eliminate it entirely. The true scale of a galaxy therefore exists partly beyond what can be directly observed, inferred through careful modelling rather than immediate appearance. As we settle into this understanding, the act of observation itself becomes part of the story. Scale is not only a property of galaxies, but a relationship between galaxies and the observers measuring them across time. The early universe is not static in our view. It is layered, with each observation revealing a different slice of ongoing change. In the next part, we will briefly consider our own position within this process, not as a source of meaning, but as a practical factor in how measurement and understanding take shape. Our position as observers is quiet but significant in the study of the first ancient galaxies. We do not influence their formation, but we do influence how their scale is measured and described. Every observation is made from a specific moment in cosmic history, using tools developed within a particular scientific context. This does not limit understanding, but it shapes its form. From Earth and from instruments placed nearby, we observe the universe along lines defined by light travel and expansion. The measurements we make are anchored in physical constants and well-tested models, yet they remain interpretations of signals rather than direct encounters. Recognizing this helps keep conclusions measured and proportional. Scale becomes something reconstructed with care rather than declared with certainty. This perspective also highlights continuity. Each generation of observation builds upon the last, refining rather than replacing. The James Webb Space Telescope is part of this progression, extending our reach without severing ties to earlier work. Our understanding of early galaxies grows by accumulation, not by disruption. As this idea settles, attention shifts away from the observer and back toward the universe itself. The first galaxies continue to exist in the record of light, unchanged by our study, while our descriptions of them slowly improve. In the next part, we will return to the broader continuity of cosmic formation, preparing to bring the narrative gently toward rest. As the view widens once more, the formation of the first ancient galaxies settles into a larger sense of continuity. Nothing about their emergence stands apart from the processes that followed. The same gravitational principles, the same flows of matter, and the same gradual adjustments continued to operate long after those earlier systems took shape. What changed over time were the conditions, not the underlying behaviour of the universe. The earliest galaxies were shaped by abundance. Gas was readily available, structures were close together, and the cosmic web was actively channeling material into growing regions. As the universe expanded, these conditions slowly shifted, distances increased, supplies became more uneven, and interactions occurred less frequently. Yet the pattern of assembly remained recognizable, extended across billions of years. Seen this way, the scale of the first galaxies does not demand special explanation. It fits naturally within a universe that builds structure through persistence rather than urgency. Early galaxies were not exceptions or anomalies. They were the first expressions of a process that continues, quietly and steadily into the present. Allowing this perspective to rest, the early universe becomes calm rather than dramatic. Its structures form, adjust, and endure, guided by forces that do not hurry. The next part will bring this motion gently back to stillness, without summary or conclusion, simply by returning to the flow itself. The true scale of the first ancient galaxies does not resolve into a single number or image. It remains distributed across time, space, and process. What we observe today is a trace, carried by light and interpreted with care, shaped by both the universe that produced it and the methods used to receive it. Nothing here needs to be finalized. The earliest galaxies continue to exist as part of an unbroken motion. They grow, merge, fade, and transform, not as isolated events, but as moments within a larger pattern that never fully stops. Scale, in this sense, is not something reached, but something continuously expressed. As this understanding settles, there is no need to hold on to detail. The universe does not require attention to continue unfolding. Its processes move forward whether they are observed or not. At a pace set by gravity and time, everything flows. Sleep in that motion,